Okay, so previously we've talked about how we can physically mix things together to make mixtures. We can get homogeneous mixtures and we can get heterogeneous mixtures. Well, it's also important to be able to separate mixtures. So there's a series of techniques that are both on the syllabus for the core papers, but also relevant in terms of like experimental work, in terms of paper 1B, that have to do with separating mixtures. Now, typically we're going to separate mixtures based on differences in their physical properties. So what are some of those physical properties? Well, the first three are all really closely related: melting point, boiling point, and volatility. So this has to do with like strength of IMFs, strength of intermolecular forces, where stronger IMF strength leads to higher melting points, leads to higher boiling points, and leads to lower volatility. So when things have differences, we can use certain techniques to separate off particular substances. Usually the ones that have more volatility and lower boiling points are easier to separate off using heat than the ones with higher ones. We're also going to have a big focus on solubility here. So by using solubility, if things are not soluble, then we can, if they're insoluble in a particular solvent, especially water, then that's useful. We can do filtration. Or if they are soluble, then maybe we can dissolve something, and then also, again, we filter it. We can then evaporate off the solvent and we can get the thing that dissolved there. There's also more subtle differences in solubility once you get into like organic chemistry. And so finding different solvents, so you can have water as a solvent, but we also have lots of different organic liquids that can act as solvents, and they all have slightly different polarities, and so different molecules dissolve into those different solvents better or worse, and so we can use that to help. These are other physical properties like color, conductivity, hardness. Those aren't necessarily going to be so relevant for the techniques that we have to learn here. Magnetism, we could use this if we have something like iron within our mixture. We could pull it out with a magnet. But otherwise, I'd say the ones at the top, boiling point, volatility, solubility, tend to be the ones that we focus on the most. So a couple of the techniques that they name, particularly on the syllabus, is solvation. So this is like dissolving something. And so this is based on solubility. So if you've got, sand, something that's not soluble, mixed with something like sugar that is water soluble, you could add water that would dissolve the sugar, and then by filtering, you could get the sugar water to one side and you could get the sand to the other side, and then you could go on to further separations. So solvation plays on differences in solubility. Recrystallization is rather complicated. It's a technique used to purify solids that you've made that have impurities, and it's also based on solubility. It's not going to be a real main focus now, but it is on the syllabus. So the idea essentially here is that you dissolve a solid and its impurities, and you pick a solvent where the impurities are more soluble. So the impurities are more soluble. And so you're able to sort of keep the impurities dissolved, and as you cool off your solvent, you get the solid you're trying to synthesize, you get it to turn into a solid first, because it has a lower solubility. So the desired solid crystallizes first. And then again, we can combine this technique with filtration, like I mentioned already, a very common one to combine. But essentially, we're able to wash away the impurities through a process of adding solvent, adding warm solvent, which dissolves the impurities and the solid, and then we cool it and we get our desired solid to crystallize first, and we're able to filter away the impurities. So that's definitely a more complex one we can talk about more in class. Evaporation is a way to get rid of a solvent and leave behind a solute. So if you've got something dissolved in water and you want to get the sugar back or the salt back that was dissolved in the water. If you evaporate off the water or the solvent by heating it, then you'll have the solute left behind. So that's kind of playing off of differences in boiling point. Something like salt or sugar has a much higher boiling point than something like water or other solvents. And so you're playing off differences. You're able to get rid of, boil off the water and leave behind the solid solute behind. Okay, filtration is typically going to use something simple like on the right, a funnel. And the funnel has some filter paper on the inside. The filter paper has very tiny holes, and so the liquid water molecules or whatever your solvent is are able to make it through, but the solid particles, whatever is insoluble, will be caught. And so we call the liquid that goes through the filtrate. You might see that language sometimes. And we should know about filter paper catching the solid. We also sometimes do vacuum filtration. A vacuum filtration setup has some kind of vacuum pump or just running water that can create suction, and that helps pull the liquid through the filter paper much more quickly. So that can be nice because sometimes the setup on the right is a bit slow. Distillation separates things based on boiling point, or you could think of it as volatility. You start to, as you can see in this picture, you start to add heat at the base of a mixture, and the classic example being water and alcohol. Alcohol has a lower boiling point, so it's more volatile, and so the alcohol will begin to evaporate off first, and it will travel up because it's now a gas, and this part is sealed so that alcohol starts to make its way down this tube. And when it goes down this tube and it gets here, you can see these tubes. These tubes are connected to a sink, and so these tubes have cold water flowing through them. So all around here, there is cold water. And that causes whatever gas is flowing through here, generally, it causes it to condense. So inside of this, there's like two tubes. There's an inner tube and an outer tube, and the outer one is full of cold water. And so this thing that we turned into a gas over here is now going to recondense, and it's going to drip down, and we can collect it down here. So we're going to separate it off. So if we start out and there's, reds and purples in here, and the red one is like the ethanol with the lower boiling point. So the red one gets evaporated, and I end up getting a more pure form of the more volatile one. And so through multiple rounds of this, you can every time you get more and more purity of this more volatile substance, and you leave behind the less volatile one is left behind. That won't be left behind completely. When you do a distillation of water and ethanol, you're almost always going to get some water going up and evaporating and then recondensing. But in general, that's the idea. There are other distillation setups. Some of them have all these little surfaces inside of them. It's called fractional distillation. And because there's so many surfaces, it causes many rounds of evaporation and condensation to take place within this chamber. And so it actually just does a better job separating things out that are otherwise pretty close in boiling point. I don't really think you need to know much about fractional distillation. It's just a sort of more advanced form of regular distillation. Okay, so these are most of the techniques used to separate things. This is a device called a separatory funnel that can be used when you're separating two immiscible liquids, immiscible meaning insoluble liquids like oil and water. So you get a higher density liquid on the bottom, you get a lower density liquid on top, and then you're able to open the valve here and pour out the high density liquid from the bottom and then leave behind just the lower density liquid on top. And sometimes you'll do this multiple times to try to just leave behind one liquid in this separatory funnel. So it's a good name. It helps you separate out liquids. And then finally, a technique that gets its own syllabus bullet point is chromatography. Chromatography is a technique Whether we're doing paper chromatography or thin layer chromatography, it doesn't really change the principles behind it, which is that we are trying to separate things out, and we're going to try to mainly use this to identify components in a mixture. Now the name comes from like separating out colors, but you can also use this to separate things out that don't have color. There's lots of different kinds of chromatography, but in our type, the example often used is with markers, which contain many different dyes. And you put this on a piece of paper. So this is chromatography paper here, this piece of white paper. And you have it sitting in some kind of a liquid, some kind of a solvent. Now that solvent is not necessarily water. In fact, it probably wouldn't be. It's often organic, or it can be a mixture of organic liquids. It really is important to get the polarity right here, because depending on what solvent you use and how polar it is, it will cause the different molecules that are in your mixture to separate out differently. The paper itself is fairly polar because it has a lot of like OH groups in it in paper and cellulose, and so the solvent, it tends to be somewhat nonpolar. And depending on how polar or nonpolar the different substances are in these, in this example, in the marker dyes, they will move up as the solvent gets sucked up the piece of paper by capillary action. The things in the marker dye also get pulled up with it. And so you've got sort of the leading edge of where the solvent gets to that we call the solvent front. And then you have how far these different dye components move. So I can see like the yellow one didn't move as much as this blue one. And then in this other color, there was a purple dye or a pink dye, and then there was a blue dye here. So there's like different components that are in there that we only see once they get separated out as they move up the piece of paper. Now, really the only thing you have to do data collection wise in chromatography is you measure how far did the solvent move. That's one distance. And then you measure how far did the spot move. And the ratio of that is something called the RF value, the retention factor. So you have R little f, and it's just the distance of your spot divided by the distance of the solvent front. So this always ends up being a value less than 1. Maybe it's, if, in this example, if the spot moved 25 and the solvent moved 40, then that's like 5/8. And so that would be like 0.625 would be our RF value. So RF values are a way of quantifying how far your spot moved, your sample moved, a component of the mixture moved, relative to the solvent front. And so you want to get like some ideal separation. Examples of poor separation would be like you haven't picked a good enough solvent or this good enough solvent, and so this one caused the dots to kind of separate out best. So that's what you're looking for. You want your solvent to be just the right amount of polarity that it pulls apart the different components of the mixtures to different degrees to help you identify them. So that's chromatography. Okay, so those are the separation techniques. You do need to know a little bit about them, what they could be used for, and we'll do some practice in class with them.